Hi, this is Andrew, and this video covers some of the basics of IPv6 for the purpose of configuring DHCPv6 in the Cisco world. This is a review, so it's not going to cover all of IPv6, but hopefully it'll be a refresher for everyone. So it's easier to start with an example. I'm going to type out an IPv6 address. Here we go. So we have 2001. And if you know IPv6, you really don't need to be watching this right now, but ultimately what I'm doing is something wrong on purpose, or something you wouldn't normally see. And let's get this font just a little bit bigger so it'll be a little bit easier for you to see. So we have 2001 0db8 ACAD, and we have 002, and now we have a lot of zeros put together, and they're broken up into blocks of 4, and then we have one final block of 4, which we're going to talk about in a minute. Is a hexdet, but it's just a block of 4 for now, and then we end it with /64. So this IPv6 address is, or all IPv6 addresses are 128 bits long. We're looking at a hexadecimal representation, which we'll talk about in a minute. First, let's look at the end of the address. We have a /64. That means that the first 64 bits represent the network portion, and the remaining 64 bits represent the host portion. Since we have 64 and 64, it's 128. That means that the 64 says it's just right in the middle. Sometimes you'll see other numbers. We're not going to worry about that right now. So now let's discuss the address, why we see it this way instead of 128 zeros and ones. Since writing out 128 zeros or ones is tedious and prone to error, and I'll show that here, if I take this and I just translate this first hexdet into binary. 2 into binary is 0, 0, 1, 0. 0 in binary is 1, 2, 3, 4 zeros. The next 0 in binary is 1, 2, 3, 4 zeros, and then we have a 1, which is 1, 2, 3, 1. So this looks longer. It's actually 4 times longer, but it also is a lot harder to keep track of. If you had to type this out, you would very easily either add a 0 or lose a 0 or mix things up. So, and that's just one hexdet. You have 8 hexdets, so you're really prone to error here. So what do we do instead? We have this address here, but so what it does is we take each hexdet and break it into 4 groups. So each hexadecimal character in here represents 4 of these binary characters. So, and then we have 4 hexadecimal characters together. Makes it a little bit easier to recognize. And each one of these can be any of 16 possible values, ranging from 0 all the way through F. And this is the way hexadecimal is represented because, let's do keep text only. So this is the way hexadecimal is represented, because we run out of digits. We have 10 digits, 0 through 9, but we need to represent 16 things. So they just move on to letters, A, B, C, D, E, and F. So that is how hexadecimal works. That's why we use it. It just makes life a lot easier in terms of typing and reading stuff. So since each hexadecimal character represents 4 bits, and we have 128 bits, that means we need 32 hexadecimal characters. And that's what we see here. We separate them into groupings of 4, which I mentioned previously, and that's called a hexdet. It's just a grouping that makes things easier to read and type without mistakes. Similar to phone numbers being broken into 3 digits, plus 3 digits, plus 4 digits. You don't put all 10 digits together and say it all as a single thing. You break it into pieces, and that helps you keep track of things. Now, if you look at this address here, you still see a lot of repetition, and we don't want all that repetition. We want to simplify it further. So what we can do is we can get rid of, one of the things we can do is get rid of leading zeros. And earlier I said you're going to see that I'm doing something that's Not correct, and this is it. We can get rid of that leading 0. 2001 dB8. Now, instead of 0 dB8, it's the same as saying we have $2 instead of we have $02. 02 doesn't offer any additional information, so we have $2. So then we add ACAD, and now with this next hexdet, we can really reduce what we're typing, what we're keeping track of. Instead of 3 zeros and a 2, we have that. Now comes a really big reduction in size. We can put a double colon, and what that does is it says any place we see a full hexadet of zeros next to each other and next to each other, eliminate all of them. And since we know how many hexadets we have, we know that if we have 5 left over when we've done that, we've eliminated 3 hexadets. Ultimately, we don't even need to know that. We just know that these are all zeros that we've eliminated. And now we have a 2 left at the end, and we don't need the zeros, so we have 2, and we type /64. So now we have a much easier address to type. So that's a global unicast address, and that can be applied to an interface of a router or theoretically to a computer. As we'll move on to with DHCP, we'll see different types of addresses there. So this is the global address. The interface will typically also have a link local address, and that is an address so that 2 devices on the same network can talk to each other, so that the computer on the network knows that if it wants to send something outside of its network, it just sends it to this address here, FE80:1. And when we do the router configuration, that router is also going to have this on its interface. It's probably going to have this address on all of its interfaces, along with a global unicast address. So now this address could be typed out as the full 32 bits also, but obviously this is just very easy to type. So as we'll see in the Cisco lab, you don't even use the /64 on the link local address because you're going to tell this that it is a link local address. You're going to, when you assign it to an interface, you're going to type link local after it, FE80:1 link local, and then the router knows that that's a link local address. So that's all I have for you for IPv6 review. Stick around and we'll hopefully get to DHCP v6 in just a minute.